Hello, everybody. Welcome again to this short course on quantum computing. Today, we'll touch upon the topic of measurement and operators. In the previous lecture, we looked into the Hilbert space point of view of understanding quantum states. So basically, we defined a two-dimensional Hilbert space, which is linear and complex in nature, and a normed vector space at the same time, wherein we can define any unique quantum state ket chi. We mentioned that we can mention or rather represent the states as vectors, rows or column vectors. We also showed that the state, the quantum state prior measurement is in a linear superposition of multiple eigenstates. Now, when we use this term eigenstate, we need to understand what exactly it means. So we say that these basis states that we have, and if we take the linear superposition of them, we get a superposition state of any quantum state, psi. But these basis states are also being called as eigenstates. So we need to understand that, which we will understand after watching this lecture. And also, we mentioned in the previous lecture, we presented a picture of what happens on measurement, right? When we make a measurement using that Stern-Gerlach equipment, the quantum state collapses to one of the basis states in a probabilistic fashion. So what we need to now understand is that so far we have seen the physical picture of a quantum state and the Hilbert space picture. We have seen the physical picture of measurement, of spin specifically. Now we need to understand how this measurement can be understood from a mathematical point of view, right? So basically, measurement of physical observables like spin and energy. So we want to measure quantities. We want to measure what is the physical quantity we want to measure. For example, we may want to measure spin. That's why we were using that Stern-Gerlach equipment. And then after measurement, we expect to get some values, right? We can also want to measure energy, and this measurement of energy is basically crucial in a superconducting qubits that we would see later. So measurement of a quantum state leads to its collapse, and all these things we have seen. Now the question that arises is that how measurement is represented in Hilbert space. This is something that we need to understand. So the act of measurement, right, in the physical world is equivalent to multiplying the state vector ket chi by an operator A. This A hat that we use is basically an operator or a matrix, in fact, right? So this A hat is a matrix that we multiply a state vector with. So the act of measurement in the physical world, so the act of taking some measurement or using some experiment, for example, the Stern-Gerlach experiment, we're setting that Stern-Gerlach equipment in the vertical direction for measurement in the vertical direction or in the horizontal direction. So the act of doing that is equivalent to multiplying the state vector with the operator A cap. Now, this operator matrix is basically different for different observables. Say we just take the example of spin. So if we want to measure spin in the vertical direction, we have a particular matrix for that. So when we multiply the state vector with that matrix, we get to the spin value that the state was in. Obviously, it collapses to one of the states, but in a probabilistic manner. But it collapses only after we multiply the state vector with this A cap. In other words, take a measurement. Similarly, if I want to measure the spin along the horizontal direction, then I have some other operator for that. Similarly, for finding the energy of the system, we have another operator which we commonly know as Hamiltonian. So some of us who have an idea of quantum physics, this Hamiltonian operator, which gives the total energy of the system, comes into the picture repeatedly. So what we are doing now is that we have operator, and we need to understand what are the properties of this operator, right? So basically, when we multiply any state vector, superposition state, or any state with this a cap, it transforms to another state. So this happens only when these operators are matrices, because whenever we multiply a vector with a matrix, it gets converted to some other vector, right? So the dimension of this A matrix, the operator matrix, is n by n for an n-dimensional Hilbert space. This is quite obvious. So basically, in our case, we use a two-dimensional Hilbert space. So the dimension of the matrix in that case would be 2 by 2. Correct? So I think this is pretty clear to everybody now. Now we come to the concept of eigenstates and eigenvalues. So this is very important to understand. Say, so far we were talking about multiplying a state vector psi, right, which is a superposition state, right, with a vector, with a matrix, and we are getting some other vector in the as a result. Now, when we multiply when we multiply the basis states we have, you remember ket0, ket1, that now we are representing as ket un for an n-dimensional Hilbert space, let's say. So let's say there is a n-dimensional Hilbert space with n basis states un. So when we multiply one of the basis states with an operator, as a result, we get the same state but with a constant coefficient. So this is an eigenvalue. So from linear algebra, from matrix algebra, you know this, that this lambda is basically a constant, which is an eigenvalue. Now, you see the difference between this case and this case. In this case, ket psi is a superposition of those n basis states, right? But when we multiply just a basis state with A, this sort of thing happens, and this is an eigenvalue equation, right? And such basis states are, that's why, called eigenstates, because they obey the eigenvalue equation. That is why a basis state is also called an eigenstate, right? So that ket0, ket1, which were the basis states of the two-dimensional Hilbert space we were talking about, is also called an eigenstate, and lambda is an eigenvalue. This is the state vector, and this is the value of the outcome that we have. Okay, this is a value of the outcome that we have. So ultimately, we need a value, right? So I'm measuring some quantity. It collapses to one state, but what is the value of the outcome I'm getting? The value is something, right? So that's something that we have. So that is called an eigenvalue, right? I think this is pretty much clear to you guys. If you find this confusing, I suggest you go back to your basic linear algebra concepts and brush them up a bit, and this shouldn't be a problem. Right? Now, another important property of these operators are the hermicity. So the hermiticity means the transjugate, or if you take the transpose and conjugate of the operators, the operator matrix, the transjugate of the matrix is equal to the matrix itself. Okay, that's the Hermitian. Now, the thing is that any operator we use in quantum computing or in our matrix foundation of quantum mechanics is Hermitian in nature. Let's see why. So first of all, these eigenvalues that we were finding have to be representing the measured values, right? And they cannot be complex. They have to be real, because any measurable quantity must be a real number. It cannot be an imaginary number or a complex number, right? So because we're measuring it. So eigenvalues are real. Now the property tells us that if the eigenvalues have to be real, the operators have to follow the rule of hermiticity. They should be Hermitian. So any operator that you take whether it's a spin operator along horizontal or vertical direction, or whether it's the, whether it's the Hamiltonian, which we would talk about later, operator, everything is Hermitian, because ultimately when we multiply any state or with the Hermitian operator, the outcome is a real number. The measured value is a real number. Yeah, the state collapses to one of the eigenstates with some probability. That is fine, but some value we are getting, right? Some eigenvalue of the measurement, that is real. Right? So remember this, that all the operators that we would be dealing with are Hermitian in nature in quantum computing. Right? Now, so since we saw that the eigenstates are basically nothing but your basically your basis states. So what we can say is that now this ket psi is a linear superposition of all your eigenstates, right? Or the basis states. This is pretty much the same. So this just goes to show that the eigenstates and the basis states are the same thing. So for an n-dimensional matrix, for an n-dimensional Hilbert space, we have n such basis states, in other words, n such eigenstates, and the entire superposition state is a superposition of all those n things, right? N eigenstates. And obviously, these eigenstates being basis states are normalized, right? So when you take the inner product between the same eigenstate, it's equal to 1, so it's normalized. When you take the inner product between two different basis states, the inner product is 0. So basically, they are orthonormal in nature. So this just goes to show that what we had discussed earlier regarding the orthonormal basis states, now the orthonormal eigenstates, right? Now, one thing you have to keep in mind that these eigenstates are not unique for different operators, right? In other words, if the operator is spin, then the eigenstates may be something else. If the operator is energy or Hamiltonian, the eigenstates might be something else. Okay. So that's what we have now. So thank you very much for watching. I think this was all about measurement and operators. So I think this much must be enough for you to get a feel about quantum computing in the later on lectures. So thank you very much for watching. See you again in the next lecture. Thank you.